Well, hi guys, we're going to do some examples of logarithms today. We're going to do some exponential growth and decay, probably the most important logarithmic application for the AP exam whenever you take calculus. So we're going to spend a full day on this one. Your exponential growth formula has an E in it, and that E is of course our number that we've been dealing with. And this formula looks like n equals n naught times e to the kt, where k is greater than 0. If k is greater than 0, that's where you're going to have exponential growth. And the n is how much it grows to, and this n naught, or n sub 0, this is like the initial amount. In calculus, we're going to write this as y equals c e to the kt power. And because we use c in calculus for something that's called an initial condition. But you might just think about this as the beginning amount. But I'm going to write that out for you anyway. This is the initial condition. Okay, the K is your growth rate. And that's going to be some big ugly decimal that you're probably not going to like. Oh, by the way, this is my shout out for Sophie. Sophie, this shout out goes for you because I love seeing your smiling face in my class every day too. So I wanted to make sure I get that in. I would feel bad at the end of the year if I didn't get your shout out in. And of course, t is going to be time. The exponential decay formula looks exactly the same. However, if things are decaying, you are losing an amount, you need a negative in that exponential graph like this. That's going to mean that your k is negative. And again, in calculus, this looks like y equals ce to the kt power. The biggest part of these problems are really you are going to need to find this growth rate right here, or the decay rate. That's going to be the hardest thing. Now, I've worked out some of these already, and I typed them up because I had to go back and forth to the calculator a lot, and so I didn't want to spend too much time on the video. So when I've got these worked out, I just got this screen shade. You're going to see what I'm talking about. Everything's worked out. I'm just going to talk you through the problem. So let's just go take a look at an example. It says at the start of an experiment there's 100 bacteria. That is like your n naught, your initial condition. If the bacteria follow an exponential growth pattern with rate k equals 0.2, so that tells you exactly what k is, A, what will be the population after 5 hours? Well, that formula is going to be pretty simple. We're just going to have n equals n naught times e to the kt power, and t is 5. And again, on this next page, I've got this worked out. And so we're going to see that here. So we just do 100 times e to the kt power. We're going to have to ask our calculator what that is. Here was our k, here was our t, and here was our n naught. And it works out to be 110 bacteria. That's a very simple application. The next question, though, says how long will it take for the population to double? Here we are trying to find the value of t, and t is up here in the exponent position. So if it's going to double, we're going to grow to 200 from 100. You see how that's doubling? And we have e to the kt power. And the question here is find t. So we're going to need to use those skills we learned in class yesterday to solve this equation. So I've got this written out, so let's go take a look at it. Okay, the first step, there's my setup. Double, so it grew to 200. The first thing I'm going to do is divide both sides by 100 to simplify this. Then the next thing we're going to do is we're going to take the natural log of both sides so that we can solve for t. This is what we practiced yesterday. We took the natural log of both sides. Then we're going to simplify this because the 0.02t comes down in front and the natural log of e is 1. You see how that's gone? Now that we've got that brought down, then we can do natural log of 2 divided by 0.02, and that gives you your time in t, and that's from the calculator. So it's going to take about 34.7, what is, I guess that's years. Is it years or hours? Let's go back and look. 5 hours, sorry, that's going to be in hours. Let's take a look at another example. Suppose a population of a colony of bacteria increases exponentially. At the start of the experiment, there's 6,000 bacteria. At the start of the experiment, 6,000 bacteria, that's your n sub 0. 1 hour later, the population has increased to 6,400. How long will it take for the population to reach 10,000? This is the first time that we are scratching our heads and we're like, hey bro, what is my value for K? It doesn't tell me this. That's the first thing you're going to need to find. So when we plug this in, the 6,400 is what it grew to. The 6,000 is what it started with, times e to the, we don't know K, but we do know the value for T. It took 1 hour to grow from 6,000 to 6,400. So what we're going to have to do first is we're going to have to find the value for K. So we're going to divide both sides by 6,000 and find the value for K. I've got this worked out here. So we plugged in 6,400 and 6,000. This is your N and your N naught. We plugged in 1 for T and we had to find K. So I divide both sides by 6,000. Then we take the natural log of both sides. Well, after it's simplified, sorry. Natural log of both sides. And that is our value for K. And it works out to be this big long decimal. Do not round this number. Don't round this number. Keep it as many decimal places as you can. A very small change in your exponent makes a great big change in your value. Okay, so now that we have that value for K, I now know my formula is N equals 6,000 times e to the kt power. So there's my formula. Let's go take a look at what the question is asking us to find. How long will it take for the population to reach 10,000? So we want to know the value for t that will make this grow to 10,000. So I haven't even answered the question yet. I just had to find the growth rate. So I've got this again, I've got this worked out on the next page. So we've got that K value, so we're going to divide both sides by 6,000, that simplifies to 5/3, and then of course natural log of both sides, and we get that we bring the exponent down, and the natural log of e of course is just 1, divide both sides by that decimal, and we get it takes about 8 years. Was that years or hours? Let's go back and look. That's not 8 years. Hold on 1 second. This shouldn't be years, should it? This should be hours. Okay. The last example is with half-life. Half-life is the time it takes for something to decay down to exactly half of itself. It says the half-life of plutonium-239 is 24,000 years. That stuff sticks around for a very long time. If 10 grams are present now, how long will it take until only 10% of the original sample remains? Round your answer to the nearest 10,000th. All right, first of all, we need to figure out what we have. We're given that n sub 0 is 10. So right now we have n equals 10 times e to the kt power. This half-life, that number is 1/2, tells me that in 24,000 years it will decay down to half of it. So what I'm going to do is I'm going to put 5 on this side because 5 is half of 10. And then I'm going to plug in 24,000 in for t. My goal here is to find the value for k. So my value for k here, I'm going to do 5 divided by 10 is 1/2 equals e to the 24,000 k power. And this one I actually don't have worked out, so we're going to work this out. So the natural log of both sides and then the natural log of 1/2 on this side. Of course the 24,000 k comes down in front. Natural log of e is just 1. And I can divide by 24,000 and I will have my value for k. So I've got my calculator up. Let's go see what that value is. Natural log of 1/2 divided by 24,000. I got it right there, I do. Okay. So this is 0.0000 then 2888. Oh, and it's negative. Why is it negative? Because we're dealing with a decay situation. So let's come back here. So this is K equals negative 0.0000, what was that, to the fifth, 1, 2, 3, 4, yeah, so what was that other number? The other number was 2888. Keep losing my marker. 2888. That's the K value. Yep. Okay. So now we have to figure out how long will it take until 10% of the original sample remains. So what I have here is that there's your value for K. 10% of the original sample would mean that it's grown down to 1 from 10, because 10% of 10 is 1. So the next thing that we do is we divide both sides by 10. Notice this decimal point 1 is 10%. And then we're going to take the natural log of both sides, do all our math there, and we get that it's 80,000 years. That's a long time for that stuff to be around. Okay, you're going to do questions like this tomorrow in class. You'll definitely need a calculator. I hope you have that, and I will see you then.